Calculus, video 28, rates of change. So in this video, I'd like to talk about the derivative as the rate of change of a function or the rate of change of an object. For example, consider a curve, right? Just some curve here. The derivative we've talked about as being the slope of the tangent line at a particular point. It's a function that gives the slope of the tangent line at a particular point. But that slope of the tangent line can also be thought of as how is that blue curve changing at that moment? Right? It's the change of the blue curve at the particular moment. We can see that at the point I've drawn here, the orange dot there, the curve is changing upward. And if I draw another dot over here, the slope is this way. We can see the curve is changing downward. For the first one, the slope is upward. The second one, the slope is downward. Or we might say that the derivative is positive on that first dot that I drew. The derivative is negative on the second dot. It describes, the derivative describes the rate at which that function is changing. Or we could also think about it as the rate at which an object changes position. Speaking of, let's go to what are considered three kinds of functions here. The position function, the velocity function, and the acceleration function. For example, suppose I have a position function that looks like this. So the position function is describing the position of an object. Think about a ball being thrown directly up into the air. Right. This position function might describe the height of the ball. So the position function here, we often abbreviate that or give the letter s. So s of t for position is equal to negative 3t squared plus 6t plus 4. Now we kind of know ahead of time here, we'll find out shortly that if this is describing the position of a ball being tossed in the air, it's not being tossed on Earth. The numbers aren't quite right yet, and we'll see that in just a little bit. So maybe we're on the moon or something like that. Okay. The question is, at time t equals 0, so t here represents time, what is the initial position? What is the position at time t equals 0? We can refer to that as the initial position. So let's think about that ball kind of idea. What we're saying. And the ball's going straight up in the air, but we want to think about that like in relation to time. And if you draw a curve just straight up in the air, you really can't see, because it overlaps itself, what's happening according to time. So we often draw it more like this, where you're picturing the ball going straight up and then coming back straight down, but we draw it over a particular time, kind of like that, where the ball is being thrown up in the air and then coming back down. What is the initial position, or what is the position of the ball at time t equals 0? Well, we see that if we were to plug in 0 into all the time values, into all the t's for the position function, we would get what's called the initial position, which is often abbreviated s naught, with a 0 there being in the subscript s naught. That is equal to s, where we plug in 0 for all the t's, time is 0. That's negative 3t squared. Negative 3 0 squared. Negative 3 0 squared plus 6 times 0 plus 4, which is just 4, and let's say we're in meters here. So what we're saying is that time equals 0 at the starting position, the initial position starts up at 4 meters. And so you're tossing the ball straight up in the air, but maybe you're standing on a plank, or something that gives you a little bit of height here, a small building or something. So we're tossing the ball, initial position of 4 meters. That's kind of about right there, so we'll call that 4. At time equals 1, what is the position? Well, to find that, we simply can plug in 1 into the time. Negative 3 times 1 squared plus 6 times 1 plus 4. Negative 3 plus 6, 3 equals 7. So we're saying there's at time 1, wherever time 1 happens to be. I kind of know the answer, so I'm going to put it right here. We see that the y value, the position of the ball, is at a height of 7. And we can do this for all the values of t, right? Where is it at time equals 2? What's the position at time equals 1.5? We can do 2. S of 2 is negative 3 times 2 squared plus 6 times 2 plus 4. We get 4, negative 12 plus 12 is 0 plus 4 is again 4. So at time equals 2, we are right back at a height of 4. Okay, so that's the position graph. The question is, next, what is the velocity function? So the velocity is the change in the position, right? So if your position is at meters, the velocity is the change in the position. It's the rate at which the position is changing, and that is a derivative. So we get the velocity function, which we call v of t, is equal to the derivative of the position function s of t. All right, so velocity, the change in the position, the rate at which the position changes, the derivative of the position. So if we go back to our position function, s of t is equal to negative 3t squared plus 6t plus 4, we take its derivative, that gives us the velocity function. The derivative of s of t would be negative 6t plus 6. So our velocity function, v of t, is negative 6t plus 6. Okay? Let's go back here. And so if you just kind of pick some points along the way here, what we're saying is the derivative of the position function is the velocity. So what we're saying is the slope of the tangent line, the slope there, that represents the velocity of the curve at the particular time. And what we're going to find out here is that time equals 1, the slope is 0. At time equals like 0.5, we have a positive slope because the ball's being thrown up. At time equals 1 second, it gets to the top at 0. And then after that, you get negative slope. Velocity is negative. Positive velocity, 0 velocity, negative velocity. At what time is the velocity equal to 0? Well, to find out what time the velocity is equal to 0, we can take the velocity function v of t. We can set it equal to 0. That would tell us what time it's equal to 0. And solve for t. So we would get 6t equals 6, t equals 1 second, and we find out that at time equals 1 second, the velocity is equal to 0. And what that represents on the graph is at 1 second, the slope is 0. Those are the possible relative extrema that we talked about earlier. That in this case, this is the maximum value of the ball. The maximum value of the ball will occur when the velocity is equal to 0. And in our case, that's at time equals 1. At time equals 2, what is the velocity? Right, time equals 2. That's this point over here. At time equals 2, what is the velocity? We're basically asking what is the slope of the curve there at that particular point. To find the velocity at 2, we come back to our velocity function, negative 6t plus 6. We plug 2, time equals 2, into the velocity function, and it will tell us the velocity at the point 2, negative 12 plus 6 is negative 6 meters per second. So we can find the velocity right at any point in time there. Question 3, or function 3, here we have what's called the acceleration function. Acceleration is the change in the velocity. It's the rate at which the velocity itself changes. So in our case, our velocity here was linear, right? So let me go back over to the top. The position function, we call that a quadratic or a degree 2 polynomial. Its curve here is a parabola, and we know that because we have a degree 2, right? Degree 2 right here. It's a negative leading coefficient, a negative 3 there, so it's an upside down or a parabola that opens down. So, but you have a degree 2 polynomial. Its derivative, the velocity function, then becomes a degree 1 polynomial or a line. Right, we have a degree of just 1, a greatest exponent of 1 here. If we were to draw the velocity function, Negative 6t plus 6, we would see that we'd start up here at 6. Negative 6t, so down 6, right 1. We see at 1 it crosses and we get a 0, right? A velocity of 0, time equals 1. This is still the time here. And we see the velocity graph is a line that looks kind of like that. That's v of t. The acceleration is the change in the velocity. It's going to be the derivative of the velocity function. So we should be able to find the acceleration simply by finding the derivative of the velocity. Picture-wise, it's going to be the slope of the tangent line on our velocity function. But because our velocity function is just a line, the slope of the tangent line is always whatever the slope of the line is, which in our case is negative 6 everywhere. So the derivative of velocity, that would be the acceleration function. So if a of t is the derivative of the velocity, which is also the second derivative of the position function, and the derivative of the velocity is negative 6 meters per second squared for velocity. Had it set up there and didn't use it. All right, a of t is negative 6. It's a constant velocity, and that's actually how it is on Earth as well. When we throw a ball up in the air, gravity acts as an acceleration function, but it's a constant acceleration. Acceleration due to gravity is a constant negative 9.8 meters per second squared anywhere on Earth, basically. It just adjusts slightly depending on altitude, but it's such a small adjustment. We basically say the acceleration due to gravity is negative 9.8. It draws it back to the Earth at negative 9.8 meters per second squared. And it's a constant. It's always what it is. So at time 2, what's the acceleration? Well, at time 2, in our particular problem, the acceleration is negative 6 meters per second squared. At time equals 1, the acceleration is negative 6 meters per second squared. It's always negative 6 meters per second squared. It is a constant, the graph of which would look something like this. Right, there is your acceleration. Constant, negative 6. Again, we aren't on Earth at the negative 6 for acceleration because the Earth has a negative 9.8, so something smaller. I don't know, Mars, or probably not quite the Moon, but it's some version of a smaller planet. Okay. Let's try one where maybe it matches more towards what we would experience here on Earth. So how about, let's let our position function equal negative 4.9 t squared plus 20t plus 5. Okay? So the curve there would look something like this. For our t-axis, we will start here at a height of 5. It'll go up, and it'll go down, right, until it hits the ground. That'll be the throwing a ball up into the air, a rocket shooting up into the sky and coming back down, right? So we can answer some questions like, what is the initial position? Oops, spell it right. Initial position. All right, initial position, S naught. That is the S value, the position value, when t is equal to 0. And if t is equal to 0, we get 5 meters. So we start at the height of 5 meters. What is the velocity function v of t? We know the velocity function is the derivative of the position function. So we'll take the derivative of the position. We'll get negative 9.8 t plus 20. All right, so there's our velocity function. What is initial velocity? In other words, at what speed are we throwing the ball up? Or at what initial speed is the rocket taking off and being launched into the air? Right? It starts at a height of 5, but at what velocity does it take off with? The initial velocity, given by v naught, is we take the velocity equation and we plug in 0 for the t's, and we get an answer of just 20 meters per second. So the initial velocity is 20 meters per second. And actually we can see that from the very beginning equation of position. When you go back to the position function, you see that this right here is S naught, the initial position when time is 0. But you also get right here, this 20 right here is V naught. And we know that because when we take the derivative, we see in this case we got for Vt negative 9.8 t plus 20. The 20 is now a constant, so when I let t equal 0, everything else drops off and I just have the 20. I can see my initial velocity from the original equation. Okay, let's go with what is velocity at time 2? What is v of 2? Well, that would be negative 9.8 times 2 plus 20. Negative 9.8 times 2 is, what's that, 19.6? Negative 19.6. And then plus 20 would be positive 0.4, 0.4 meters per second, which is really close to 0, which is telling me that 2 is probably going to be about right here. It's a positive velocity, so we think that the curve is still going upward here. The slope of the tangent line is still positive. Yet, it's almost to 0. It's almost to that peak, right, where we get that maximum value. All right, let's see. What is that maximum value? Let's first of all, at what time do we get that max value? At what time is the velocity equal to 0? All right, at what time is the velocity equal to 0? Well, we'll take our velocity function, negative 9.8 t plus 20. We'll set it equal to 0, and we'll find out what time the velocity is equal to 0. Solving, I get 9.8 t equals 20. T equals 20 divided by 9.8. 2.05, somewhere about 2.05 seconds. At 2.05 seconds. So what we're saying is at 2.05 seconds, we get a horizontal tangent line, a velocity of 0 from the position function. Right? This function we've drawn here, that is the position function. Okay. So what is the height that occurs there? Well, if I want to know what is that maximum height, the maximum height in this case, so the ball is going up and then coming back down, the maximum height will occur at when that velocity is 0, which occurs at 2.05 seconds. So I would need to go back to my position function, because that's what tells me what my height is. There it is. To my position function, s of t is equal to negative 4.9 t squared plus 20t plus 5. Plug in the 2.05 to find the height at the maximum height, the height when the velocity is equal to 0. Okay, we'll just say what's the max height? In this case, that is a relative extrema, a relative maximum. That will occur, go back to the position function, s of t, negative 4.9 t squared, I believe it was plus 20t plus 5. So s of 2.05 is negative 4.9 times 2.05 squared plus 20 times 2.05 plus 5. Let's see, 2.05. But it'll help if you can type it in the calculator correctly. Okay, that was long and drawn out, but I got 25.4. 25.4, it's a max height, so meters here. Right, so the max height up here, somewhere about 25.4 meters. All right, let's go to the acceleration function. The acceleration function a of t is equal to the derivative of the velocity function. So acceleration function, we'll take the derivative of velocity function, negative 9.8 t plus 20. Its derivative is negative 9.8. That is the acceleration due to gravity on Earth, meters per second squared. Acceleration function. It is a constant negative 9.8. So no matter what time we're at, if time is 2, acceleration is negative 9.8. If time is 4, acceleration is negative 9.8. It's the same negative 9.8 for all of time. Good. Let's try just graphing these one more time. So we had our initial graph. Our s of t function looked like this. Our velocity function, negative 9.8 t plus 20, right? Negative 9.8 t plus 20. Let's start up here at 20. Negative 9.8, it's going to come down like this. And we know it's going to cross here. The velocity is going to be 0 at 2.05, we found out. Right, velocity is 0 at 2.05. In other words, we're going to have in this region here between 0 and 2.05, we're going to have positive velocity, or we might say that the function is increasing. Velocity is positive. And from 2.05 until it hits the ground, the function will be decreasing, or we might say the velocity is negative. And then the acceleration function, negative 9.8 is just a nice horizontal line, a of t at negative 9.8. Very good. Sometimes we get kind of tired of just using quadratics for position, which quadratics does describe the parabola, right? Does describe the position of an object. And the reason it describes the position of the object, and the reason we know it's a parabola, is because of this. We know that on Earth, the acceleration due to gravity is constant. It's a negative 9.8. So if the acceleration is constant, and the acceleration is the derivative of velocity, that means the velocity has to be linear. Right, go to the velocity here. It has to be linear. The derivative of a line, right, the derivative of linear, take the derivative there, you get a constant. So if acceleration is constant, that means the velocity must be linear. And if the position, or if the velocity is the derivative of the position, that means the position must be a quadratic, because the derivative of a quadratic, went too far up. The derivative of a quadratic is a line, right? Is a degree 1 polynomial. We'll go from a degree 2 to a degree 1. So we know that the position function, by throwing a ball up into the air, must follow a quadratic or degree 2 polynomial path, right? Because we know that the acceleration due to gravity is constant. But like I said, sometimes that gets old, and we start talking about things like particles, which don't necessarily follow all the rules of gravity. And so we can just create our own different functions for position, such as negative t cubed plus 18t squared plus 100. Okay, let's start here. What's the initial position? What is S naught? Hopefully you said that's 100 meters. Or centimeters, whatever we're talking about. I didn't give you units, but let's just go with meters. Okay, what's the velocity function, vt? That's the derivative of the position. That's negative 3t squared plus 36t. All right, what is the initial velocity? v naught. Well, that one, there's no constant here. So whenever we plug in 0 into the t values, we get an initial velocity of 0 meters per second. What is the acceleration function, a of t? That's the derivative of the velocity function. That is negative 6t plus 36. And what is the initial acceleration? This time there will be, that the acceleration is a line, it's linear, so it's going to be different at different times. But at a naught, when t is equal to 0, we get 36 meters per second squared. Okay, and then we could ask questions like, well, what is the velocity at time equals 2? And to do so, you'll just take 2 and plug it into the velocity function. And get for negative 12 plus 72 looks like 60 meters per second. How about this? At what time, or times, at what time or times is the velocity function equal to 0? Right? What we're looking for here are those relative extremists, the max, the min, the relative max, the relative min. So we'll take our velocity function v of t, we'll set it equal to 0. So negative 3t squared plus 36t equals 0. Hopefully the first thing you do is factor out maybe a t, or even better, a negative 3t, leaving you with t minus 12 equals 0. And the zero factor property says I can take negative 3t and set it equal to 0. I can also take t minus 12 and set it equal to 0. If I solve each of these, I get t is 0 and t is 12. So at t equals 0 seconds, the velocity is equal to 0. At t equals 12 seconds, the velocity is equal to 0. So what do we mean by that, right? So go back up to the position function. The position function is a cube, is a degree 3 polynomial, but it's a negative leading coefficient. So it's gonna look something like this. Negative leading coefficient, degree 3 polynomial. I'll change this in a minute, but it's gonna have some basic looking thing, look something like that. But let's see if we can make it more accurate. Let's see if we can draw the position function a little bit better. Here's what we know so far. We know that at time 0 and time 12, the velocity is 0. So we're expecting it to flatten out at that point. The position function should have a 0 slope at those points because the velocity is equal to 0 at 0 and 12. We know that the initial position is 100. So at time 0, the position is up at 100. At time 2, we know the position is, the velocity is 60, so it's a very large slope. Velocity is the slope. The slope is 60. We know that the velocity is 0 at time 0, and the velocity is 0 at times 12. So maybe not a ton to go off of, but we can see this. We can see that at time 0, the position is at 100. We know it's a negative cube graph, and we know also that at t equals 0, the velocity is equal to 0. So it's going to flatten out there. So it's going to look something like this. It's going to come down, going to go back up. At 12, it's going to flatten out as well, right? So at 0, we should have a slope of 0. At 12, we should have a slope of 0 as well. And you get a curve that looks something like this for our position function, s of t. If the position function is a degree 3 polynomial, then the velocity must be a degree 2 polynomial, because the velocity is a derivative of the position, so you're taking the derivative, power rule, you're bringing the exponent down and subtracting 1 from the exponent. So a degree 3 goes to a degree 2. So if we were to draw the velocity function, v of t, we would see that v of t is equal to 0 at 0. V of t is equal to 0 at 12. And if I go back up here, we see the velocity function is negative 3t squared plus 36t. It's a parabola opening down. So a parabola opening down that I know goes through 0 at 0 and 12 is going to look something like this. All right, so that would be the velocity function. How about the acceleration function? The acceleration function, right, Well, we could know ahead of time the velocity function was a degree 2 polynomial. Take the derivative to get to acceleration, and now you have a degree 1 polynomial, which is a line. If you go to the acceleration function, it is negative 6t plus 36. Acceleration function in this particular case for this particle, which doesn't have to follow these rules of gravity, so different acceleration might be different depending on the different time. It was 36, I forgot it now. Acceleration right here, negative 6t plus 36. Negative 6 down, so down 6 right 1, down 6 right 1 means it's going to cross here at 6. Just a little bit. Right, that is our acceleration function. And we can see that the acceleration will equal 0 whenever time is 6. If time equals 6, acceleration is 0. That actually makes a lot of sense. If you go back to the velocity graph, remember that the acceleration is the derivative of the velocity. So the acceleration, the derivative of velocity, means that the slope of velocity should have a slope of 0 when time is equal to 6. The acceleration is equal to 0 when time is equal to 6. Okay, very good. That is all that I have for position, velocity, and acceleration.